Today, we're diving into some fascinating research that's proposing a whole new blueprint for artificial intelligence, and it's one that's inspired directly by, you guessed it, our very own brains. You know, we live in this era of incredibly powerful AIs, right? They can write poems, they can generate these jaw-dropping images, but they still feel, well, a little alien. They don't have that flexibility, that common sense we all just take for granted. So that brings us to the big question for today. With all this incredible computing power, why aren't these AIs more like us? To get to the bottom of that, we first have to talk about the basic limitations of today's AI models. Think of it as a kind of glass ceiling they keep hitting. So on one side, you've got current AI. Yeah, it can be brilliant at very specific tasks, but it's also incredibly brittle. You change the rules just a tiny bit and the whole thing can fall apart. It's also super inefficient, needing just insane amounts of data and energy. And then you've got the human brain, which is basically the exact opposite. It's flexible, it can learn from just a few examples, and it's amazingly robust. And here's the crucial point. We can't just keep throwing more computer power at the problem, hoping it'll fix itself. The problem isn't about getting bigger, it's about a fundamental difference in the design. The way AIs are built today is just a completely different architecture from how our own biological intelligence is put together. So if the design's the problem, where do you look for a better one? Well, the answer is pretty obvious, right? It's the brain. It's had millions of years of R&D, and this research suggests it has two key secrets that AI has been missing out on. Okay, secret number one is something called functional specialization. Your brain isn't just one big supercomputer. It's more like a team of specialists. You've got distinct systems for different jobs. You've got your perceptual systems processing what you see and hear, your executive systems up in the prefrontal cortex making the big decisions, and then these auxiliary systems that kind of regulate and fine-tune the whole operation. But having a team of specialists is only half the battle, right? You need them to work together, and that's secret number two, how they communicate. The brain uses these things called neural oscillations. You might know them as brain waves. They're these rhythmic electrical pulses that coordinate everything. The best analogy is an orchestra. The oscillations are like the conductor's tempo, making sure every section comes in at exactly the right time. And there you have it. Specialized parts and rhythmic timing. These are the two key ingredients from biology that most AI architectures have pretty much ignored. So this brings us to the really cool part of this research, a brand new AI model that actually builds these two biological secrets right into its code. It's called the Tripartite Brain-inspired architecture. And yeah, it's a bit of a mouthful, but the name tells you everything you need to know. Tripartite means three parts for those specialized systems, and brain-inspired, well, that part's pretty clear. Let's break down what those three parts are actually doing. First, the perceptual system. That's like the eyes of the AI, taking in all the raw data. Then you have the executive system. That's our conductor, putting all the information together to make the final call. And here's the game changer, the auxiliary system. It's the rhythm section, generating those oscillations that sync everything up. So you see, this is way more than just another neural network. By building in these simulated brainwaves, it's designed to coordinate its own thinking in a way that's way more dynamic, more, well, brain-like. It actually has a pulse. Okay, so this all sounds amazing on paper, but you're probably thinking what I'm thinking. Does building an AI this way actually make a difference? Does it work? Well, the results are in, and honestly, they're pretty staggering. This isn't just a small step forward. It's a huge leap in how smart and efficient an AI can be. Get this. The model needed almost 49%, nearly half, fewer computational steps to make a decision compared to other top models. That is a massive gain in efficiency. It's not just working harder, it's literally working smarter, deciding on the fly how much thinking it needs to do. And now you're thinking, okay, if it's that much faster, it must be less accurate, right? Nope. This efficiency doesn't sacrifice accuracy at all. On tough image recognition tests, like one called CIFRAF 100, this tripartite model was actually more accurate by up to 2.18% while using way less computing power. It's literally the best of both worlds. But numbers on a chart are one thing. Here's where it gets really interesting. Does this new design actually capture something about the way we think? Does it behave in a more human way? Amazingly, the answer seems to be yeah, it does. When they tested it to see how it handled uncertainty, the model's patterns of confidence were a much closer match to actual humans than previous AIs. What that means, in plain English, is that it tends to get confused by the same tricky things that confuse us. So let's just recap the results here. The model is more accurate, it's vastly more efficient, saving a ton of energy, it's more robust, so it handles messy, real-world data better, and maybe the coolest part, its thought process is more aligned with our own. That is one heck of a report card. So, what does this all mean for the future of AI? Well, the implications of an architecture like this go way, way beyond just getting better at classifying pictures. What's so cool is that we can actually peek under the hood and see the model think in real time. When you visualize its internal activity, you see this clear rhythmic process. It starts with its different parts highly synchronized, paying broad attention. Then, things desynchronize a bit as it digs into the complex details. And finally, it resynchronizes as it locks in on a final decision. That rhythm is incredibly similar to what we see in our own brains. And that's really the biggest takeaway here. Even though they tested it on visual stuff, this isn't just a neat trick for image recognition. The researchers see it as a whole new foundational framework, a new starting point for building more general, more flexible, and more efficient AI that could tackle language, reasoning, you name it. The ultimate goal, and they say this right in the paper, is to create systems capable of bridging the gap between artificial and biological cognition. This isn't just about making better calculators. It's about moving AI from pure number crunching to a more holistic, dynamic form of intelligence. Which leaves us with a final, really fascinating question to think about. We've seen what happens when AI can compute on a massive scale. But what becomes possible when AI doesn't just compute, but starts to truly coordinate? Imagine robots with fluid, common-sense reactions, or software that anticipates what you need with an almost intuitive rhythm. The future could start to look and feel very different.